And let me open the camera here and make sharing for the screen. طيب السلام عليكم ورحمة الله وبركاته. Can you see the slides now? Welcome back to microprocessor class. This is, I believe, lecture 23, if I'm not mistaken. صح كده ولا إيه؟ Okay, so this is lecture 23, microprocessor class, and we are in the last two lectures, we motivate for floating point. We discussed the floating point standard presentation, the IEEE 754, and today we continue with that standard, elaborate more on the range of values that the floating point give me, and which motivates more or show you, demonstrate to you how useful is the floating point compared to the integer numbers or fixed points. And then we will go to discuss some challenges for the floating point, which is the arithmetic operations. In this class, we will demonstrate and discuss only addition and subtraction for floating point, similar to what we did for DLD. So you can consider this lectures, these three lectures, as a kind of extension to what we learned in DLD chapter 1, but for a totally new representation, which is called the floating point. And inshallah, next lecture, we will discuss what is the hardware that actually can support the floating point, how it works, and we'll give a little bit of the architecture details and the organization of the x87 core processor, and we will discuss very briefly some of the instructions for these kind of processors. You have to start solving problems from assignment number 5, which is related to the floating point. You have to know how to convert from decimal to floating point and from floating point to decimal using the IEEE standard. As you may see in the examples for the assignment number 5, we will not be using all the time the two officially announced standard for IEEE 754 of 32 bits and 64 bits. We may use a less number of bits for that, but the concept is the same. As we mentioned before, you have to keep in mind that the number should be normalized and the exponent should be biased. You have to know how many bits for the Mantissa, fractional Mantissa, how many bits for the exponent, and definitely the sign of the Mantissa. In the last set of slides that we covered in the last lecture, we have left the last example. Let's go over that example. We are in slide number 26. Slide 26 is actually asking you to represent in single precision representation the IEEE 754 for single precision, which is actually 32 bits. Okay, we need to represent the number which is in decimal 639.6875. Okay, if this is my example, I want to convert this into floating point, single precision floating point, lower 32 bits. As we mentioned in the last lecture, the 32 bits, the single precision 32 bits contains 23 bits for the fractional Mantissa, okay, 8 bits for the exponent, bias the exponent, and 1 bit for the sign of the mantissa. Okay, remember that the mantissa is represented using sign magnitude. The exponent is represented through 2's complement after biasing. It's biased 2's complement. Okay, so as the steps that we have already explained in the last lecture, the first step for putting the number into the floating point representation is to convert the number from its decimal representation to its binary representation. Can you see the number here? So you can do this conversion through the calculator, through any of the methods that you already learned in DLD. Okay, so you can use recursive divisions for the integer, recursive multiplications for the fraction, and then you will have the number ready in binary. So after converting this to binary, I get 1 1, as you see here, 1 1 1 1 1 1 0 0 1. Okay, I have here 1 2 3 4 5 6 7 8 9 10 bits for the 639. Okay, for the integer part, 0.1011 for the fractional part. Okay, here this is the normal conventional conversion for the real number in binary. Is the number now ready for the floating point or not? نخلي كده نسأل شوية أسئلة عشان نشوف الناس صحية معانا ولا نايمين ولا إيه الأخبار. تمام؟ What shall I do? The first thing that I do now, I get the bits of the number. What is the first step? نعمل إيه؟ مين يرد؟ Normalization. بالظبط يا مها. So I have to normalize. How to normalize? I have to shift the decimal point, okay, to the left or right. I have to shift it to the left. How many places? I have total of 10 bits. Okay, I need the last one to remain, okay, for the shifting. After the shifting, I'm shifting 9 bits to the left. When I shift numbers to the left, I am raising the powers of A. Where is the powers of A? The powers of, احنا هنا بنتكلم على binary. So I'm raising the powers of 2. For how many times? For 9 times. So the number in the exact same number can be represented as 1.001111111101 multiplied by 2 to the power 9. This is the exact same number as the original, but right now I have 1 point. I put it in the format 1 point something. Okay, so now the IEEE standard is asking me to do 2 things. Okay, no need to waste the 1 bit for the most significant bit, which is always 1 in terms of binary. So we will discard this and we will take the fractional mantissa to be placed in my storage. A fractional mantissa that's to be stored in the 32 bits, starting from the first 3 bits here. Okay, I have 23 bits. Okay, take the first 3 bits here, 0, 0, 1, put them here. Then 4 ones, put them here. Then 1, 1, 1, 0. Second bucket of bits, and finally here the number contains only 2 ones. Okay, so I will have those 2 ones. So actually remember that I need only 9 bits to store the fractional mantissa for this. It's 9 bits, 9 from the integer, which is now fractional, and we have 4 here. If 9 plus 4 is a total number of bits that I have for the fractional mantissa from the number itself. The number occupies how many bits? 9 coming from the integer originally. Everything right now is fractional. And 4 coming from the original fraction. Right now, the total fractional mantissa is how many bits? 9 دول والاربعه دول على بعض يدوني كام هنا؟ كام بت هنا؟ How many bits for the fractional Mantissa after discarding the first one؟ ها؟ كان عندي 10 و4 discarded the first one, so I end up of مين اللي قال 31؟ How many for this number? How many bits do I need for the fractional Mantissa؟ عدهم يا شباب، كانوا 9 جم الانتجر و4 كانوا اساسا في الفراكشن، يبقى التوتال كام؟ لا حول ولا قوه الا بالله. 9 و4 كام؟ 13. I have 13. يبقى this number actually needs 13 bits in the fractional Mantissa. Okay, starting from the most significant bit of the fractional Mantissa, I have 13. 3 plus 10. 3, then 4, then 4, then 2. طيب. الفراكشنال Mantissa in the single precision floating point of IEEE standard has 23 bits. So what shall I do? I have to extend the number to the right with zeros. Get منين الزيروز دي؟ Just to complete the 23 bits. The original number needs 13 bits to be occupied. ادي 13 bits. هضيف عليهم كم؟ 10 bits of zeros. يبقى I have to extend the number with 10 bits of zeros here in order to complete the 23 bits. 13 جايين لي من النمبر و10 هضيفهم من عندي اصفار on the right. When I add zeros to the right of the fraction, I do not change the value of the number. We learn this in DLD. Make sense ولا does not make sense؟ صح ولا ايه؟ Agree? Any questions? So عرفنا ال 23 bits جم منين؟ ال 23 bits of a fractional Mantissa. After converting the number actually has 14 bits. The most significant one is always discarded. I have left for me كام؟ 13 bits. 13 bits now after the normalization is actually all fractional. يبقى كله هيتحط في fractional Mantissa. Starting from the first in the fractional side 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, then 1, 1. Then complete the 23 with 10 zeros extended to the right. Make sense? عرفنا الفراكشنال Mantissa جت منين؟ Any questions? Any doubts? Shall we move on؟ اهي الفراكشنال اهي 13 بت اهو اتحطوا هنا اترصوا. What's next؟ Exponent. By the way, what about the sine bit? The sine bit is, by the way, it belongs to mean sine bit, although it is placed in the floating point IEEE standard as the most significant bit of the number. Okay, it belongs to the fractional Mantissa. The fractional Mantissa comes with the low 23 bits. And then followed by 8 bits of the exponent and the 1 bit for the sign of the Mantissa. يبقى المانتيسا total for the Mantissa 24 bits. 23 bit for the fractional Mantissa and 1 bit for the sign. And they are not placed together in the floating point. Okay? 23 bits are the low significant bits and the sign is the most significant. ومحشور في وسطهم in the middle is the 8 bits of the exponent. Agree? Make sense? Sine is stored as the most significant bit of the 32 bits in the memory. I have 32 bits stored in the memory. The most significant bit is for the sign of the Mantissa. طيب. Well, least 23 bits are for the magnitude of the Mantissa. تمام? And in the middle, I have the biased sine 2's complement exponent. Agree? Make sense? Any questions? Can we move on? Okay? We finish the Mantissa. Fractional and sine. Now what is left for us؟ بقى لنا ايه؟ بقى لنا مين؟ الاكسبوننت. بالظبط كده يا رغد. الاكسبوننت بنعمل ايه في الاكسبوننت؟ We have to bias the exponent. How to bias the exponent? If I have 8 bits of the exponent, that means I use the rule 2 to the power n minus 1 minus 1. This is the amount of biasing. We mentioned it last time, okay? So that means the biasing for this representation is 127. 127 should be added to the exponent. I have to add 127 to the exponent. The exponent originally can be 9, add 127 يديني 136. The exponent should be represented as the number 126 in binary. So I will take the 136 and convert it from decimal to binary. Okay? I will end up of 001, 0001, 0001. This is the mean, this is the exponent. So I will take the exponent and store it here for the exponent field. 0001, 0001. Okay? This is the 32 bits of this single precision floating point representation for the original decimal number as we see above. Agree? Make sense? Any questions? Any doubts? Now, a number in binary will be actually 10 zeros, then the bits of the number ending at the bit 23 for the Mantissa, and then I have the 8 bits for the exponent and the bit for the sine. If I want to see this in hexadecimal, so remember that I have for total 32 bits. 32 bits represented by how many hexa digits? In شاطر يقول لي how many hexa digits we need here for the number 32 bits? 8. برافو عليكم. تمام. 8 is grouped in buckets of fours. يبقى هنا بقى هبتدي من least significant bit او من most significant، مش هتفرق. Take the first 4 zeros، يبقى binary اهو وادي الهكسا بتاعه. Then 4 zeros، then 0011 C، then 0111 E، then 1111 F، then 100. Now the exponent bit, the Mantissa bits are finished. So I will take one bit from the exponent with the 3 bits of the most significant bits of the Mantissa to build this bucket, the bucket number number 6. 1000 means 1 in hexa, then 0010 for the exponent from the second bit to the fifth اللي هي هتبقى 0010 يبقى دي 4. وبعدين finally the last 3 bits of the exponent 001 مع الساين بت يدوني الباكت الاخرانيه اللي هي برضو تديني 4. Agree? Make sense? Any questions? Easy? Simple? طيب جميل. Now remember that putting the number in floating point, okay, is a very big advantage, but this complicates the hardware of dealing with the numbers. If the numbers is already in floating point, performing the mathematical operations is much more difficult. Okay, nothing comes for free. That's why to do arithmetic for floating point is not easy. We will only learn the simplest thing, which is the addition and subtraction. But to do multiplications and divisions, okay, this needs one full class to explain to you how to build hardware that actually can do floating point multiplication and division, which out of our scope. We will take the addition and subtraction as just an example to demonstrate to you how things can be done in floating point, to make the idea much more clear for you. Before we go to the arithmetic operation, addition, subtraction, we need to start the next set of slides that actually starting with what? Starting with give you some information about how the numbers are being, some more details about how the numbers are being represented in floating point in the computer system, the standard IEEE standard, and also to give you some idea about what we gain out of this. What is the range of values right now? Okay, this is the first thing to learn. We know that, so we will take the single precision floating point IEEE standard as our example to demonstrate how things are changing when we go to floating point from the integer. Do you still remember the integer? Now, if I have, for the single precision, how many bits do we have? We agree that the single precision floating point is 32 bits. ماشي الكلام؟ 32 32 bits. طيب. If I have 32 bits and I want to represent, using them to represent sine numbers. So the sine representation is the 2's complement. مش كده ولا ايه؟ We usually use the 2's complement. What is the range of values for 32 bits in the 2's complement integer? يعني if I am using the 32 bits for integer numbers, what is the range? The general rule بتقول لنا ايه؟ minus 2 to the power n minus 1 لغايه 2 to the power n minus 1 minus 1. We learned this in DLD. ما حدش يقول لي ده جت منين، تمام؟ Go and review DLD. If you have 32 bits and you are using the sine 2's complement, the range of values is from negative 2 to the power n minus 1 to positive 2 to the power n minus 1 minus 1, which is actually give you the range of values from minus 2 to the power 31 to positive 2 to the power 31 minus 1. Agree? How many combinations of numbers here? Now I am utilizing, okay, 32 bits for the number, and I'm utilizing all of them for only integers. تمام? How many combinations? طبعا integers, half of the range, as we learned in DLD, half of the range is for the negative, half of the range is for the positive. صح كده؟ تقريبا. طبعا الزيرو والبوزيتيف. How many total combinations of numbers do we have for 32 bits? Number of combinations of numbers. يبقى الرينج عندي من ايه؟ من minus 2 to the power، مظبوط كده يا مان. It's 2 to the power 32 اللي هم يطلعوا كام؟ 4 billion، okay, or 4 multiplied by 2 to the power ايه؟ 4 مش 4 بقى بليون بنقول 4 ايه؟ 4 ميجا نمبرز، 4 ايه؟ مظبوط كده، رقم كبير قوي. تمام؟ 4 بليون كومباينيشنز، 4 بليون اللي هم ايه؟ 124 multiplied by 124 multiplied by 124 تمام multiplied by 4 تمام. يبقى I have more than 4 million okay combinations of number. Okay, that's a lot. Sure, this is a lot, but actually the most important thing that we need to highlight here is the range of values. For the sine 2's complement, I have only integers. I have positive and negative, but starting from minus 2 to the power 31 لغاية positive 2 to the power 31 minus 1. Now let's go for the fun. What about the floating point? IEEE standard single precision. What is the range of values? Okay, this is a very interesting question. Now, before we answer this question, we need to highlight some special cases. We need to highlight some special cases. In the floating point representation, okay, we have to reserve some values for some extreme numbers. Not all of the 4 million combinations are used. Okay? For integer, I'm using all of the combinations. للأرقام من minus 2 to the power 31 minus 1 للpositive 2 to the power 31 minus 1 minus 1. Okay كده؟ طيب. For the single precision, not all of those 4 billion are used. But I'm still having a much better utilization for the different combinations of ones and zeros. I have much bigger range of values when I represent the number in floating point. Before we go to that, we need to discuss some reserved combinations. ايه هم reserved combinations? This table that is shown right now to you is showing some special values for the exponent, E here for exponent, and F here is for the fractional mantissa. Okay? When I have all the exponents zeros, all mantissa, fractional mantissa zeros, this is reserved for the number 0. And we have two representations for 0. We have positive 0 and negative 0. ليه؟ مين صح يقول لي؟ احنا عندنا هنا في الفلوتنج بوينت حاجه اسمها negative 0. Yes, mathematically it's meaningless, but it do exist. ليه؟ لأن I am putting the mantissa in sign magnitude. And for sign magnitude, I have the sign bit to represent the sign. Sign bit equals to 1 means negative, equals to 0 means positive. If I have either positive or negative zeros represented. ازاي I represent negative or positive 0? All the exponents should be zeros, while all fractional should be also zeros. Fine. And this is the first special case. The second special case is this one. اللي هي ايه بقى؟ I can represent in floating point the number infinity. They reserved combination for the infinity. How to represent infinity in floating point? I have to put all the exponent to be ones and all the fractional mantissa to be zeros. This is a reserved combination. Reserved لمين؟ Reserved للinfinity. تمام؟ يبقى I'm reserving all zeros and zeros for the 0, and I am reserving all ones or exponent and all zeros for the fractional mantissa to the infinity. Fine. If the mantissa, if the exponent is all ones, okay, and no matter what is the value of the fractional mantissa, those are not numbers. يعني you cannot interpret any of those combinations. By the way, those are a lot. Those, how many combinations here? Yes, you can do when you do when you do x over 0, okay? When you do x over 0, this is infinity. مش كده؟ تمام؟ Or an invalid, usually بنقول لهم invalid number or infinity. Yes, that's actually possible in the floating point. I have a representation for infinity, for sure. طيب. هنا بقى, طيب, if the exponent is all ones, okay, and the fractional mantissa contains anything except zeros, all of those range of values are not a number. Okay, there is no interpretation of their meaning. Okay, by the way, those are a lot, so I'm actually excluding out of the 4 billion combinations a significant amount of numbers that are excluded. اللي هم ايه؟ لما يكون الاكسبوننت عندي كله وحيد ولما يكون الفراكشنال مانتيسا anything except the zeros. All of those I cannot convert them back to decimal. They are meaningless to me. They are called them not a number. NaN. تمام كده؟ Agree? طيب. The second special case is of when the exponent equals to all zeros and the mantissa equals to anything. Okay? Those are valid numbers, but we call them an unnormalized numbers. Unnormalized means we are not following, okay, the rule of excluding the most significant one, okay, and putting the decimal point to the most significant position. Okay, we will discuss the unnormalized numbers inshallah during this lecture. تمام؟ طيب, to cut the long story short, exponent all zeros or exponent all ones are for special cases only. يبقى to have the normalized numbers, the exponent should not be either all zeros or all ones. If I exclude the first value and the last value of the exponents, I reserve them for those four special cases. واضح الكلام؟ Agree? طيب. Make sense? حد فاهم حاجة؟ كله متابع معايا؟ Now, remember something. The exponent has how many bits? We are talking about the single precision. يبقى exponent takes the values, okay, or the combinations from all zeros لغاية all ones. احنا reserve already all zeros مع fractional Mantissa all zeros للرقم 0. All zeros مع x in the fractional Mantissa is for what we call the unnormalized numbers. طيب, we also reserve all ones and zeros to infinity. We resolve all ones of the exponent and the x in the fractional Mantissa to not a number. So this left for me only for the exponent starting from 1 0 0 0 وبعدين ال 0 1 0 0 0 وبعدين ال 1 1 0 0 0 لغاية ال 0 1 1 1 1 1 are all the range of normalized numbers. صح كده؟ What is the value of the exponent for each of those? خلي بالك, remember something, the exponent is biased. يبقى when I have the number 1 0 0 0 in the exponent, this convert to which value? Real value in decimal. ثانية واحدة يا شباب. تمام؟ احنا قلنا ايه؟ ان الاكسبوننتس اوريدي بايزد، مش كده ولا ايه؟ صح؟ يبقى I wanted to, if I want to retrieve the number back, I wanted to take the exponent value and subtract mean 127، مش كده ولا ايه؟ يبقى the real value of the exponent here, if I have in the exponent 1 0 0 0 0, the real value of the exponent is minus 126. كله متابع؟ طب what if the exponent has the value 2? The real value is minus 125. Are you following me? صح؟ مش كده ولا ايه؟ Agree? Make sense? طيب لما يكون الاكسبوننت فيه 1 1 1 1 1 1 1 0، ال 1 1 1 1 0 دي اللي هي الفاليو كام؟ 127. All ones except the first bit, the most significant bit. دي ال 127 اطرح منها 127 يديني كام؟ 0. Are you following؟ صح؟ مش كده ولا ايه؟ Agree? Then the largest number ever here for the exponent for the normalized numbers is 0 1 1 1 1 1 اللي هو كام؟ ده كام بالديسيمال؟ مين شاطر يقول لي ده كام بالديسيمال؟ 0 1 1 1 1 1. الديسيمال الفاليو بتاعت ال 0 1 1 1 1 بالديسيمال يطلع كام؟ هو ايه اللي 15 ده؟ 15 ازاي؟ انا عندي 8 بيتس يا هند، حرام عليكي، انا كده هتجلط. 8 بيتس 0 1 0 وبعديه 7 وحايد. ايوه كده عبد العزيز، 254 مش كده؟ 254 يبقى the maximum exponent for the normalized numbers is 254. تمام؟ هنرجع نطرح منه 127 يديني كام؟ 127 برضه. مش كده ولا ايه؟ يبقى for normalized number the smallest exponent is minus 126, where for the maximum value of the exponent is 127. يبقى range of values for the exponent starting from minus 126 للpositive 127. That's why my biasing was 127, لأن لما أجمع 127 على الأرقام دي هيديني الرينج of values from 1 لغاية 10000 لغاية ال 01111. Agree? Make sense? We are in slide number 6 in the chapter 7 set of slides. Chapter 7 floating point arithmetic. We are in slide number 6. We are explaining what is the range of exponents and what's the range of values that I have. Right. For normalized numbers, do you still remember the equation to convert back the number? We mentioned this equation in the lesson. Minus 1 to the power s multiplied by 2 to the power the exponent minus 127 multiplied by 1 point fractional Mantissa. In order to convert any number in those representations, this is the equation. تمام كده؟ طيب خلاص اتكلمنا على reserved 000 وال 1111 for the exponent. طيب ايه بقى حكايه ال unnormalized numbers؟ Unnormalized numbers, we don't want to lose, okay, the significant amount of representation for the numbers. When the exponent equals to all zeros, okay, we call the number is unnormalized. And the difference here in two things. We do not add the 1 for the fractional Mantissa, and we assume that the exponent is the minimum ever. The minimum ever exponent minus 126. يبقى equation for unnormalized is minus 1 to the power s, 2 to the power minus 126, multiplied by the fractional Mantissa directly, without adding the 1 to its most significant position, to the integer part. تمام? Agree? Fine. Based on this, can we now, are we ready now to calculate the minimum fraction that can be represented in floating point and the largest number that can be represented in floating point? The answer is yes. And this is what we will be explaining next. Now, for the simple precision, I have 32 bits for the fractional Mantissa. Okay? What is the smallest? What is the largest? What is the largest number ever I can represent in floating point? I have to have the maximum exponent and the maximum Mantissa. صح؟ مش كده ولا ايه؟ The maximum number that can be represented in floating point has the maximum value of the exponent and the maximum value of the Mantissa. Are you following? طيب. What is the maximum exponent? The maximum exponent is 01111 لسه مناقشينه دلوقتي تمام. The largest exponent ever is 127. Great. تمام. طيب. What is the largest possible Mantissa? Largest possible Mantissa when I have all the bits of the Mantissa are equals to 1. تمام. So what will be the value of the fractional Mantissa in that case? The value of the fractional Mantissa in that case will be, I can convert this through the من binary للديسيمال. بس في تريك سهلة قوي. If I add 1000000 to this number, I will end up of the number 1. يبقى this الفراكشنال مانتيسا value here is 1 اللي احنا اساسا بنشيلها plus the value of this. What's the value of this? It is 1 minus 2 to the power minus 200 2 to the power minus 23. Okay, يبقى الماكسيمم fractional mantissa ever is actually 2 minus 2 to the power minus 23. طبعا ال 2 to the power minus 223 is very small number. So this the value of the fractional mantissa is almost 2. مش كده ولا ايه؟ صح؟ يبقى ال value of the fractional mantissa is almost 2. تمام كده؟ ليه؟ لأن 2 to the power minus 23 ديت is very small number. يبقى ال maximum fractional mantissa is almost 2. طيب حاضر. خلوني بقى أعملها على السبورة. What is the largest ever number in floating point? What is the largest ever number? The largest exponent 0 1 1 1 1 1 1 1. اتفقنا ان ده الفاليو بتاعته هتطلع كام؟ ومحدش يقول لي ليه مش 1 1 مش كلها وحاجه، لان احنا we excluded الاول ones للانفينيتي. مش كده ولا ايه؟ agree؟ يبقى الفاليو بتاع دي كام؟ 2 اللي هو كام؟ 127 after unbiasing. اخد ده واعمله unbiasing. صح؟ يبقى الماكسيمم exponent is 127. طيب what is the maximum fractional mantissa? When I have all 23 bits ones اللي هم ايه؟ 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 23. صح؟ 23 بيت كلهم محايد. تمام؟ ادي 4 8 12 16 ها 20 وبعدين 3. All of them are ones. طيب تعالوا ايه let's go and dissect this 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 111. Okay, I want to retrieve the number back. بنعمل ايه؟ Okay, 0.0. يبقى this is the fraction, the biggest fractional mantissa. طيب في تريك هنا. يبقى I need الايه؟ الفاليو largest fractional mantissa. largest fractional mantissa. تمام؟ هجمع على الرقم ده خلاص another number 0 with 22 zeros plus 1. يعني عندي هنا 1 في ال least significant bit. عندي هنا 22 صفر وواحد في البيت ال 23. Okay? If I added this to both sides, حد يقدر يعمل لي الجامعه دي؟ تطلع كام؟ ها؟ هيطلع كام ده؟ adding 1.00000001 ده يطلع كام؟ 1 plus 1 is 0 وكاري 1 وكاري 1 وكاري 1 وكاري 1 هيطلع كام ده في الاخر؟ ايوه كده نفس الشرط. This is actually the number 1. طب والناحيه الثانيه largest fractional mantissa plus this number. طيب what is the value of this number؟ النمبر ده عباره عن 1000 كام؟ وعندي 22 صفر. Okay, what is the value of this? مين شاطر يقول لي؟ When I have a number that has all zeros, only have one bit of 1 at البت رقم 23. خدناها في دي ال دي. ها؟ How can I get the value of this? ها؟ ايوه كده بالظبط، لان الفيرست زيرو here it's order -1 واللي بعده -2 -3 -4 لغايه this bit has the order -23. يبقى ال value of this number equals to كام؟ 2 to the power -23. Agree? Agree? Make sense? يبقى إذا the last fraction Mantissa equals to this is 1 وهنقل الناحية الثانية. يبقى 1 minus كام؟ 2 to the power -23. But remember something, in fractional Mantissa we already excluded 1 out of it. كان في واحد هنا واحنا شلناه عشان نحطه في الفلوتنج بوينت. There was a 1 here and we excluded. Okay؟ يبقى إذا المانتيسا مع value الماكسيمم value of the Mantissa is adding 1 to this. يبقى 2 minus 2 to the power -23. Okay؟ اللي هي almost 2. Right. Now we get the largest exponent ever. We get the largest Mantissa ever. What is the largest number after all of this? The largest number ever is actually 2 to the power 127. Remember, this is an exponent multiplied by 2 minus 2 to the power -23 اللي قلنا ان ده تقريبا باثنين اللي هو يطلع تقريبا almost كام بقى؟ 2 to the power 128. Agree? Almost. لان دي very small fraction. صح؟ Do you agree؟ زوم in اكتر من كده. Can you see? I'm adding this to the two sides to make this easy. بدل ما هتحسبي دي ازاي؟ This is just a trick for the calculation. Okay? You don't want to do this trick? Go الله معك بقى روح احسبي هنا دي -1 -2 -3 -4 اجمعي بقى كل دول يبقى 2 to the power -1 اجمعي على 2 to the power -2 اجمعي على 2 to the power -3 لغايه 2 to the power -23 جمعي ده كله هتطلعي الفاليو دي. بس انا عملتها بتريك صغيره كده عشان اسهل الحسبه. جمعت عليها I added to this 0 0 0 0 1 here. ليه؟ دي كده اتحولت لواحد ودي حسبتها سهله. It's just a trick, a mathematical trick in order to give you this. Okay? If you are not convinced, go and make the powers of 2 here. -1 -2 -3 -4 لغايه -23. عايزه تحسبيها بالطريقه المباشره احسبيها بالطريقه المباشره. اقعدي فيها ساعه ونص. انا عملت تريك عشان احسبها. عبد العزيز فين؟ شوف اللي مش فاهم يعرفها زي ما هي. مش هقدر اشرح اكتر من كده. This is just a mathematical trick to get the equation. At the end of the day, what is the largest value that I can represent in floating point? The largest value ever with the largest value of exponent, the largest value of Mantissa is 200 to the power is 2 to the power 128. طيب, let's go back to the integer. What is the largest value ever for integer? حد لسه فاكر؟ For integer. قلناها النهارده. The largest كام ال largest؟ لا حول ولا قوة إلا بالله. الانتجر, what is the largest integer? What in the integer? If I am utilizing those 32 bits for integer numbers, what will be the largest? Largest integer. لو أنا بستخدم ال 32 bits الانتجر sine to complement, what is the largest value? أيوة كده. 2 to the power, لا 2 to the power 31 minus 1 sine to complement. Even حتى لو أنا بتكلم على unsigned numbers هتبقى 2 to the power 38 32 minus 1. Okay? Can you compare between the largest number in integer and the largest number in fraction in floating point? هنا the largest number is 2 to the power 31 وهنا the largest 2 to the power 128. 128. Can you see how efficient is the floating point to represent large numbers? And the same thing even more for the fraction, as we will see. تمام؟ نرجع منين للسلايدز. طيب. Now, for the smallest number, the smallest number ever I can represent, the smallest number ever I can represent in floating point is not for the normalized number, it's for the unnormalized ones. ايه unnormalized دول؟ Unnormalized are using the smallest exponent. What is the smallest exponent ever? We are in slide 6. ايه the smallest value for the exponent? For representing fractions بقى. The smallest exponent ever is لا ماشي لا اما الاكسبوننت بيبقى size far ده احنا when the exponent equals to all zeros we do not we consider this an unnormalized number. تمام كده؟ طيب what is the value of the exponent at that case؟ بالظبط كده يا لبنى 1 minus 126 يبقى ال smallest exponent ever minus 126 يبقى الفاليو بتاعته 2 to the power minus 126. طيب what about the fraction? How can I get the smallest fractional Mantissa ever for unnormalized numbers? unnormalized numbers مفيش جمع للواحد هنا. There is no one added here. Okay? يبقى ال smallest fraction ever هيبقى بكام؟ based على اللي انا عملته على السبوره. مين يقول لي بقى؟ مين شاطر يقول لي؟ What is the smallest fractional Mantissa ever? مظبوط كده يا هاني. What's the value of this? It is the fractional Mantissa that has all zeros except the least significant bit of the fractional Mantissa. This is the smallest fractional Mantissa ever. صح؟ يبقى what is the value of this fractional Mantissa? الفراكشنال Mantissa ever the smallest اللي هي when I have all zeros except the least significant bit has the value 2 to the power minus 23. يبقى the smallest fraction Mantissa ever is 2 to the power minus 23. The smallest exponent ever, now we are in slide 9. Okay, the smallest exponent ever when I have the exponent equals to all zeros, we assume that the exponent value here is minus 126. يبقى the total بقى the smallest possible fraction that I can represent it here is ال 2 to the power ال 23 minus 23 for the Mantissa and 2 to the power minus 126 for the exponent. يبقى the smallest number ever that I can, for smallest fraction ever that I can represent numbers in the accuracy of 2 to the power minus 149. This is very small infinitesimal fraction. Okay, so to cut the long story short, okay, slide 10 here is actually showing me the range of values, positive and negative, for the floating point, the largest ever and the smallest ever. Okay, so I can represent numbers up to maybe 2 to the power 120, not ever 27 but 28. okay، يعني هنا مش بس 27 ده كمان 28 لان الفاليو بتاعت الرقم ده كده هتطلع تقريبا 2. تمام، as we agree. اوكي، في البوزيتيف وفي النيجاتيف. and the smallest fractional ever can be 2 to the power minus 149. Agree? A range of values for the floating point is not continuous. Okay, when you are representing fractional small numbers, the representation of numbers are closer to each other. When I go to the integers and the big integers, the spaces between the representation is getting larger. تمام؟ يبقى I do utilize still the 4 billion combinations for the 32 bits, but in a completely different fashion. Here I can represent very small infinitesimal fractions or very large integer numbers for using the floating point. The spaces between the representations is not even, not equal to each other, unlike the integer, and the range is way bigger. Agree? Make sense? حد فهم حاجة؟ Clear? طيب. The second thing that we need to discuss is actually, يبقى احنا كده خلصنا discussion. This is was to give you an idea about how the numbers are, the range of values represented in floating point is different from the range of values represented in integer. Okay, spaces between the still I have discrete 4 billion represent, not even 4 billion. I excluded not a number, big range of values, and I'm actually representing either very small fractions or very big integers. Okay, through the floating point. طبعا الماجيك هنا, because I'm not storing the exponent as it is, I'm storing only the power, which powers of 2 for the exponent part. Right. The challenge that we wanted to discuss next is actually the challenge of the mathematics. Okay, performing addition and subtraction for floating point is different than the addition and subtraction that we learned in the regular binary, because right now the numbers are represented in the computer system in floating point. So in order to demonstrate the challenges here, we need first, as I usually did, starting by an example from the decimal. تمام؟ يبقى أنا هدي example للديسيمال عشان أوضح الidea. What are the challenges that you have and what is the correct technique to perform the addition operation. طيب, assume that I'm talking about storage and slots in decimal. هنرجع تاني للديسيمال. Assume that I can represent numbers or can store the numbers in decimal. Assume that I have 4 slots for the Mantissa, or for the digits of the Mantissa in the decimal. يبقى 4 digits can be stored for the Mantissa, and 1 digit is stored for the exponent. Okay, I have the following 2 numbers, 99.99 and the number 0.161. Assume that I wanted to store these numbers. Okay, how can I store these numbers? Okay, without going into too much of hassle for the biasing. Forget about the biasing. So I can simply normalize the 99.99 to be a 9.999. تمام? Assuming that the decimal point will be a after the first bit or the first storage, يعني first digit. يبقى I can those four digits will be stored in four locations اللي هم 9999. تمام؟ 4 slots. Where the exponent here will be stored as it is. هنا طبعا since I shifted the decimal point one place to the left, I have to raise the powers of 10 لأن احنا بنتكلم على decimal. Okay? يبقى ال exponent here will be stored as a number 1. You agree? Make sense? Make sense? Fine. Right. What about the other number? The other number is 0.161. To put it in normalized format for the decimal, I have to shift the decimal point to the left or to the right عشان نبقى in using the same convention between the two numbers. So I'm shifting the decimal point to the right. I'm shifting the decimal point to the right. I have to lower the powers of 10 بقى. صح؟ يبقى this could be represented as 1.610. طبعا I extended here with 0. تمام؟ يبقى the number will be stored as 1610 for the 4 digits of the Mantissa, and for the exponent I will just store the value -1. Remember something, these five storages are enough to store the number, as you can see here. Okay? The first number actually has 4 significant digits. The second number has only 3 significant digits. صح كده؟ Agree? Make sense? Right. Sorry. Right. What if I wanted to add those two numbers? Even for this example, as it is decimal example, I can recognize the problem. Can you add those two numbers together? 99.99, I will add it to 0.161. What shall I get? شايفين الريزلت هنا؟ The result of adding those two numbers should be mathematically كام؟ 100.151. Agree ولا مش agree? Do you agree on the result ولا لا؟ صح؟ Yes, you agree. طيب جميل قوي. Can you notice the problem here? The original two numbers can fit in the 5-digit storage, 4 for the Mantissa and 1 for the exponent without any problems. But after the addition, can I store the result back in the same 5-digit storage? What is the Mantissa? El-Mantissa هنا contains how many digits? Can you see how many digits do I need to store this Mantissa exactly as it is? I need how many digits? I need 6 digits. Okay? So that means although the original numbers fits perfectly in the storage, after the addition I may do what we call rounding. I may start losing some of the significance of the digits. Okay? So can I still store the numbers? The answer is yes. Okay, the result, the answer is yes, but I cannot store it exactly as it is. I have to round it a little bit. To fits mean to fits only. مش صح قوي يا هند. ال 5 rounded عادة we are rounding the 5 up. صح مظبوط. Okay. يبقى this number should be stored as a 100.2. صح كده؟ طيب. So I think now you start admiring the problem of the mathematics. The first problem of the mathematics is the rounding. تمام كده؟ طيب. Let's go into the steps of performing the addition in floating point even for this example of decimal. if I wanted to store the numbers, remember that right now I have my numbers represented as the example here. تمام؟ يبقى actually let me just let me go to the board here to make the idea more clear. Can you see my board? Now I wanted to demonstrate to you for this decimal example, how can I add the numbers? If I have 4 slots for the numbers, okay, assuming that the decimal point is here, okay, we agree that 99.99 will be represented as 999, and its exponent equals to كام? The value 1. طيب البوint 0161 will be point 0 and point 161 will be represented as 1610. والexponent بتاعها بكام؟ 1 -1. Now we shift gears. This is what we have in our storages. واضح؟ Agree? نتشاف كده؟ Can you see this? طيب جميل. Now if somebody asked me to add, so forget about the original numbers. انسى بقى the original numbers. I want now to add those numbers that are stored in my computer system. Assuming that the computer system can store the numbers in decimal. What shall you do to perform the addition? Will you go right away and start adding the digits of the Mantissa together? Can we add the Mantissa together directly? The answer is no. Why I can't add the Mantissas together? Because there is power difference between them. How can I recognize the power difference between them? How can I recognize the power difference between them? Go and check Go and check the exponent. Okay? So I have, my first step is to equalize the exponent. The exponent should be equal in order for me to be able to add those two numbers. So how can I make the exponents equal? This is actually equalizing the exponent is called alignment process. I have to align the numbers, okay, by making the exponents equal. Now, what is your ideas? How can I align the numbers, okay, to prepare for the addition? Exactly. I have to shift a decimal point, or actually shifting the number. مين فيهم اللي يتشفت? Shall I shift this or shift this? Remember something, they are stored in the computer system. So shall I shift a bigger number or the smaller number? Okay? Remember, if I shifted the bigger number, okay, to make, actually I have first to compare between the two exponents. How many difference between the two exponents? So I have to subtract البيجر من السمولر. يبقى 1 minus minus 1. How many difference between the two exponents? 2. يبقى the first step is to subtract the exponents from each other or compare the exponent to each other. How many difference you can get between them? You get 2. That means there is a 2 places difference between the number, the first number and the second number. طيب, which one do you expect to shift? Are you shifting the number, the decimal point for this to the left to make this bigger, or shifting this? هتعمل alignment لمين فيهم? If we shifted this to make it like this, I will lose the significant digits of here. مش كده ولا ايه؟ صح؟ يبقى I have to shift مين؟ the smaller. يبقى alignment يبقى by shifting the smaller exponent أو the smaller number, the smaller Mantissa, the smaller number أو shifting a number with smaller exponent can be number of places equals to the difference between the two exponents. يبقى النمبر ده هيتشفت to the right. معنى كده ان الديسيمال بوينت بتاعته هتتشفت to the left. Okay, how many places? A number of places to make the two exponents equal. One shift for this to the left will raise the exponent by 1. تمام؟ طيب, another shift will make the exponent here ايه؟ يبقى one shift will erase it 1. Are they equal? لا مش equal. يبقى I have to do. يبقى I have to do 2 shifts to this number. يبقى هنا shifting this decimal point 2 places. Okay, will actually the first shift هتعمل ايه الفيرست shift؟ 0 1 6 1. الباور هنا بقت كام؟ بقت 0. Are those equal? Are those equal? Not equal. يبقى I have to do it again. تمام؟ I will do another shift. 0 0 1 6. In the second shift, remember something. I started already losing bits. يبقى ادي اول rounding. اضطريت اعمله. I have lost the least significant bit of the small number due to the alignment between the two exponents. Now the exponents are equal, and I started losing part of my significance of the result. يعني ايه lose so much? Do you have any other way to do it? This is the storage that you have. Okay, these are the numbers and you want to add them. يعني ايه ألوت ولا مش ألوت؟ Do you have any other solution? عندك أي حل تاني؟ مفيش حل تاني. Okay, I have to shift the smaller exponent, the number with the smaller exponent, number of times to the left. Okay, to match. يبقى I have to do match الإكسبوننت. الإكسبوننت لازم يتماتشوا. مش هعرف أجمع من غيرها. I cannot add without matching the exponent. Then I will perform the addition. تعالوا نجمع. Let's add the numbers. 9 و6 يديني كام؟ 5 و1 كام؟ 1 و9 و1 يديني 1 وبعدين هنا 1 و9 و0 يديني 10 0 و1 و9 و0 يديني 0 و10. اوكي الاكسبوننت عندي لسه كام؟ agree؟ يبقى first I did the rounding. I use sum of bits from the smallest number and then I added the numbers. Now, is this ready for storage? Remember, how many slots do I have for my Mantissa? Where is the decimal point? The decimal point here we agree to be right after the first digit. يبقى first match the exponents. Second step is perform addition. Right. After I do addition, I wanted to store this in the available storage. في حد عنده أسئلة هنا ولا؟ Do you agree? Any questions so far? يبقى دي step number 1. Okay? Then دي step number 2. Step number 3 بقى أعمل إيه؟ I have to normalize the result because this does not follow the standard that we agree upon for the number. Okay, we agree that to have number integer point fraction, integer point fraction. Even this also should have only one digit for the integer. يبقى محتاج أعمل إيه؟ Normalization again. Okay, so I have to shift the decimal point. How many places بقى? How many places? A decimal point here, in order to follow the same standard I agree on, should be shifted one place to end up of the same convention, like the numbers stored here. Okay? When I shift the decimal point to the left, بيحصل ايه؟ I am raising the power of the exponent. يبقى finally the number here is 1 والبوينت اهي زي ما هي 0 0 1 وفي عندي هنا 5 هتطلع بره will be kicked out. That's why I need to do ايه؟ I need to do ايه؟ I need to do ايه؟ Rounding. برافو يا هند. I have to do another rounding here. الخمسة دي أطردها وامشيها وخلاص؟ لا. I have to use a some way of a mathematical scientific rounding. الخمسة بتراوندed up. يبقى I have to do rounding. يبقى step number 3 another normalization. Normalize result. I have to normalize a result, and during the normalization, including possible rounding. Include possible rounding. A rounding here in 5 هتبقى ايه؟ 5 1 rounded up هتبقى 2. يبقى actually, can we retrieve the result back? This is what will be stored in my computer system. Okay, I store the first number, I store the second number. Now, after storage, I want to, in order to add those two numbers together, I have to first match an exponent by shifting to the left the decimal point of the smallest exponent number of times to match between the two exponents. Second, do the addition. Third, normalize the results, including rounding. Okay. Now, can I retrieve back my answer? The answer عندي 1.002 multiplied by 10 to the power 2. اللي هو actually كام؟ It is 100.2 بالديسيمال. Now, check in mathematics did I get when I do this in pen or pencil? This addition give me the answer as 100.151. Okay, this is the original correct absolute answer. But in the computer system, I get the answer rounded. Okay, so this is actually what we want to want. So these actually the steps that we will be following to perform the add operation. Okay, matching the exponents, perform an addition, normalize the results. Okay, we will continue in next lecture. في ناس عندها حصة عايزة تمشي. Okay, but here we will stop here. We in this decimal example, in the next lecture, inshallah, we will explain the how can we do the exact same thing. It is the exact same concept, by the way, with the 3 steps. Nothing is new, but we will just perform this on binary instead of decimal. But the technique and the steps are exactly the same. Thank you, and see you next lecture, inshallah. Thank you. Let me stop recording here.